You are draining your pool. All of a sudden, the sky opens up and a torrential downpour ensues. Meanwhile, Susie is skydiving and her parachute won't open. She decides to aim for your pool. Will there still be water in the pool when she lands? 8 minutes later, will she live? Initial water height equals 4 feet. Pool dimensions equals 8 feet by 10 feet. Rate of water in equals 2 gallons per minute. Rate of water out equals 20 gallons per minute. The goal of this problem is to determine if Susie will land in the pool with water left in it. To determine this, we are going to go to the macroscopic mass balance. We have a mass coming in, the torrential downpour, at 2 gallons per minute, and a mass going out, because we're draining the pool, at 20 gallons per minute. So we go to the macroscopic mass balance. We have accumulation is equal to the mass in minus the mass out. We can substitute in the mass change is equal to rho, the density, times the volume flow rate. So we have rho times the change in the volumetric flow rate over the change in time is equal to the density times the volumetric flow rate in minus the density times the volumetric flow rate out. We can then substitute the dimensions into our the change in volumetric flow rate, so that it accounts for the change in height. So we have the length, which is 8 feet, the width, which is 10 feet, and the dH, which is the change in height. So we plug that in, so now we have length times width times the change in height over the change in time is equal to the volumetric flow rate in minus the volumetric flow rate out. Now you see that we got rid of the densities because we assume that it's a constant density because it is an incompressible fluid. So all the densities cancel out. And then next we divide by length and width. So now we have 1 over length and width times the change in volumetric flow rates is equal to the change in height over change in time. Now we bring the dt over to this side, and then so we separate the variables, and then we're going to integrate. So on this side we have the change in height integrated from initial height h1 to final height h2 is equal to 1 over the width times the length times the change in the volumetric flow rate. All these terms are brought outside the integral because they're not changing with respect to time. Okay, and then we have no term for time, so it's just the change in time from initial, which is 0 seconds or minutes, to t, time in minutes. After we integrate, all we have over here is h, all we have over here is t. So we have h from h1 to h2, so you go final minus initial, h2 minus h1. Over here, everything remains the same, and we have t from t to t0, so we have t minus 0. All we have left is t. Then we're going to solve for h2, our final height. So by adding h1, so we have our final height will be equal to the initial height plus 1 over the base of the pool times the change in volumetric flow rate times the time. So we plug in our values. So we have initial height 4 feet plus 1 over the base times, again we're going to plug the volumetric flow rate in gallons per minute, 2 gallons per minute. We're converting it to feet cubed per minute minus the volumetric flow rate out, gallons per minute, times feet cubed per 7.48 gallons. That is the conversion from feet cubed to gallons. And then we're multiplying by 8 minutes, which is how long it takes for her to reach the pool. And when you plug everything in, you find that there is only 3.76 feet of water left in the pool.
Coming to you live from Angola, Indiana for the 5 o'clock news. We have an instance of Susie. Susie was trying to skydive and her parachute did not deploy. She fell into the neighbor's pool. Well, she would have died anyways, but she hit the side. The pool was just too shallow.